This Franz-Keldysh effect works because applied electric fields fundamentally alter semiconductor optical absorption. The clever bit here is quantum wave functions leaking directly into forbidden energy gaps when exposed to voltage gradients. When a strong electric field energizes a bulk semiconductor crystal, standard electron plane waves transform into distinct, mathematically defined shapes known as Airy functions. These mathematical Airy functions possess spatial tail distributions that extend deep into the classically forbidden bandgap zone of the solid-state semiconductor lattice. Because electron and hole wave functions leak into this gap, optical photon absorption can suddenly occur at photon energies well below the normal material threshold. Fermi's golden rule proves that greater spatial overlap between these tailing wave states directly intensifies the optical absorption taking place inside the semiconductor volume. When experimental physicist Carl W. Boer first detected this optical absorption edge shift inside high-field domains, historical record-keeping and naming faced immediate complications. Boer originally named the phenomenon the Franz effect after German physicist Walter Franz, who had independently derived the initial theoretical framework predicting band edge shifts. However, Russian physicist Leonid Keldysh had concurrently derived the exact same quantum mechanical equations using an independent theoretical approach during that exact same timeframe. Because Keldysh's seminal paper was published in Russian, Western research has faced a temporary language barrier, delaying widespread international recognition of his parallel work. Furthermore, early theoretical models completely omitted exciton binding effects, which actually dominate optical properties near the fundamental semiconductor bandgap. This missing exciton physics meant early mathematical predictions struggled to match precise experimental absorption spectra near the semiconductor absorption edge. A few months later, when the English translation of Keldysh's paper became available, Boer promptly updated literature to formally name it the Franz-Keldysh effect. Physicists refined the underlying quantum models by thoroughly mapping how electric fields transform electron wave states into spatially asymmetric Airy functions. These decaying Airy tails overlap even when electrons and holes sit at slightly different physical locations along the applied electric field gradient. As a direct result, the absorption spectrum exhibits a pronounced absorption tail below the bandgap energy, accompanied by characteristic quantum oscillations above it. By incorporating exciton interactions alongside field-induced tunneling, theorists finally created a complete, physically accurate model of bulk semiconductor electroabsorption. This solid theoretical framework confirmed that uniform bulk semiconductors could dynamically control optical transmission simply by modulating internal voltage fields. The bigger problem was that triggering significant Franz-Keldysh absorption in bulk semiconductor materials typically required hundreds of volts across the crystal. Standard modern microelectronics operate at tiny low-voltage logic levels and cannot supply hundreds of volts without experiencing catastrophic electrical breakdown. For high-speed fiber optic communication systems, requiring massive drive voltages made bulk electroabsorption devices thoroughly unviable for practical silicon integration. Engineers initially pivoted towards quantum-confined Stark effect modulators, which operate at lower drive voltages but require complex quantum well semiconductor structures. Quantum wells demand ultra-precise atomic layer epitaxy, severely driving up manufacturing costs and lowering production yields compared to simple bulk semiconductors. Optoelectronic engineers desperately needed a way to harness cheap, uniform bulk Franz-Keldysh materials without forcing modern microchips to deliver hundreds of volts. Engineers solved this fundamental voltage scaling problem by abandoning open-beam bulk transmission and adopting an integrated optical waveguide geometry instead. In a waveguide geometry, an incoming optical laser carrier is tightly confined within a microscale semiconductor channel along its entire propagation distance. Instead of passing light perpendicularly through a thick bulk slab, light travels horizontally down an extremely narrow active semiconductor core. By placing electrical control contacts mere micrometers apart across this narrow waveguide channel, enormous internal electric fields are created using minimal drive voltage. Because electric field intensity equals voltage divided by distance, submicron electrode spacing converts standard low-voltage logic signals into ultra-strong field gradients. As the guided light wave travels along the waveguide channel, it continuously interacts with the field-induced absorption tail over the entire channel length. This extended interaction length along the optical path compensates for lower drive voltages, dramatically enhancing overall optical signal modulation depth. Applying a small digital voltage pulse causes the semiconductor waveguide core to rapidly shift from optically transparent to strongly absorbing. When the control voltage returns to zero, the airy wave function tails collapse back into standard plane waves, instantly restoring light transmission. Electroabsorption modulators utilize this precise waveguide design to seamlessly convert high-speed electrical data signals into modulated laser light. Because uniform bulk materials are used rather than delicate quantum wells, these waveguide modulators offer superior yield, durability, and cost efficiency. Detailed laboratory testing confirms that intense optical power guided through these engineered microchannels maintains stable, high-speed switching without thermal instability. The Franz Keldysh effect demonstrates how fundamental quantum mechanics turns field-induced wave function leakage into an essential modern optoelectronic control mechanism. From Walter Franz and Leonid Keldysh's groundbreaking theoretical derivations to Carl Bohr's high-field domain discoveries, quantum physics accurately predicted real bandgap tails. Although 100-volt operational demands once hindered bulk semiconductor implementation, clever waveguide architecture completely unlocked practical low-voltage commercial hardware. By confining guided light inside microchannels featuring microscopic electrode spacing, engineers achieved ultra-fast electroabsorption modulation with standard microelectronic signals. This elegant combination of field-induced airy wave functions and integrated optical waveguides underpins the high-speed electroabsorption modulators driving modern optical networks. Quantum wave functions extending into forbidden energy gaps provided the core physical phenomenon, and smart waveguide geometry transformed high-voltage physics into global internet infrastructure.